All right, there we are finally. Welcome everybody. Sorry for the slight delay. I hope you can hear me all right. I know the sound's kind of tricky. Hi, I'm Jan. Today I want to talk about downsampling in Prometheus. I'm quite excited about this talk. Actually, a bit too excited as it turns out. I got a little carried away. I read my proposal after the fact and needed to make sure that I'm actually talking about what I promised I would talk about, but I think it's close enough. So downsampling, I think in Prometheus is pretty old feature request, right? I think first came up in 2017, and the answer was, yeah, we don't do it. But it's a pretty interesting topic. That's sort of, I think, one of the main motivations here to talk about this. And I also can talk a little bit about signal processing, which is super cool. So why not, right? And as you can see, there's another topic I can relate this to that I'm reasonably excited about. So yeah, that was sort of the motivation. And I recently did some work with this at my day job at Red Hat, which unfortunately doesn't leave me too much time to work on Prometheus. So, it was a nice coincidence to take this here. So yeah, that goes to say I'm quite excited about this talk. All right, what are we going to do today? So we'll talk about downsampling, sort of what that actually means. It's a pretty broad term, and when it's requested in sort of Prometheus and systems like that, it usually means a subset of what it could mean. So we need to sort of define what we want to talk about, right? We will talk a little bit about what works in Prometheus today already, what everybody can do. And then I will, I wanted to show you a little example, the experiment I was trying to do. There's still a bug, so I don't have too much to show, but there's a couple of things I can already sort of tell you about. Okay, so downsampling. What do we mean when we say downsampling, or what might others mean? So this is a term that comes from the land of signal processing, specifically digital signal processing or discrete signal processing, and it's really super ubiquitous, right? Here in this room, all these machines, there's probably tens, if not hundreds, of sample rate conversion processes going on right now, right? The sound, all the video, it's really everywhere. The sort of the goal is usually fewer samples. That could be a reduction in bandwidth. So if you think Prometheus, think labels, or sample rate, right? Just how often you have samples for a particular series. And yeah, sample rate conversion is really ubiquitous. It's even Prometheus is unthinkable without sample rate conversion. If you think about scraping itself, right? If you change the scrape interval, you're essentially doing a sample rate conversion on your metric. Recording rules could be considered resampling or downsampling. And if you ever look at any graphs, be it in Prometheus UI or in Grafana, there's definitely downsampling going on there. So yeah, really, Prometheus is already what they call a multi-rate digital processing system, if you want a nice term for it. And so one subset of sample rate conversion or downsampling in the signal processing world is often called decimation. So decimation by an integer factor means you throw away a bunch of samples, right? So you keep every second, every third, every 10th sample. And that sort of goes already in the direction that we want to talk about, right? So here is sort of an outline of what I think people mean when they say downsampling in Prometheus. We usually talk about the time domain. There's no reason we have to talk about the time domain, right? The downsampling across labels is actually quite powerful, but that's not what I will talk about today, really. You can already explore this with recording rules, right? That does downsampling across label dimensions very easily. Just wanted to say we talk about the time domain usually, or I will in this talk, and that's sort of a different subset. And the goal, yeah, is usually store fewer samples. You want to save some data storage, right? But maybe you don't want to do this right away usually. So there's usually a delay expected. You want to have, like, for a day or two, you want to have the full resolution, and then later you want to have fewer samples. You might want to select interesting samples. We'll see about what that could mean and what you can do there. I'm specifically talking about algorithms today that select samples, whereas you could also do downsampling by computing new samples, right? You can compute averages, you can sum things up. You can do this already with recording rules today too. Sort of the selection of samples works in recording rules too, of course, but maybe with limitations, let's say. Right. So with this, one thing I'm not going to talk about today, but it's kind of adjacent, is parametric retention. This is actually an even older feature request. That's from 2016. That often has the same sort of goal in mind, where people want to keep some samples around for longer, for like seeing long-term trends, but not everything. I think it's still an interesting feature to discuss, and sort of, again, has the same goals or similar goals, but ultimately it's a very, very parallel feature, if you will. So we could have both of those and they could work in concert, but ultimately they're adjacent to each other. Okay, so let's maybe look quickly what I mean. So we have a counter, right? And then we want to, after a time, downsample it. So we want to throw away these gray dots. Let's see, this looks okay. Yeah, and you see the first couple of samples there, we keep at the full resolution, and then later we throw some away. So this doesn't look too bad for a counter, right? We could even throw away a couple more, and we still sort of get a resemblance of the data. We could run rates over these samples, and they would largely be the same, you know, if you do the rate interval long enough, because they're, of course, accumulating, which is nice. I'm pretty sure histograms work the same way as this. They're not as easy to visualize, so I really don't talk about them that much. But I'm pretty sure histograms should be easy too. If you do a gauge, you know, things start to look a little tricky. So this is only decimated by the factor of 2. So we throw away every second sample, whereas the counter was already decimated by 4, right? So we keep only every 4th sample. If we go to 4, things devolve even more. So yeah, doesn't look great. And this is where sort of the discussion comes in over what could be an interesting sample, and maybe we want to keep some other stuff than just the sort of latest in a time bucket, or, you know, just count out every 4th sample and keep that blindly. But we make a quick detour and want to talk about how you can do downsampling today in Prometheus already. And maybe can have a quick show of hands. Who here does downsampling already? I think there was like 5 or 6 hands. It's another one, 7, okay. It's a good chance that actually a lot more do it. So you have really two ways of doing this. One is with federation, right? You have one Prometheus that's here on the left. That's, yeah, it's your left too. That scrapes at, you know, say 15 seconds. Retention there would be typically pretty short. And then you have a second Prometheus instance that scrapes the federate endpoint of the first Prometheus, but it only does so every 5 minutes. You pass a match expression to get the samples that you want. Don't put just a wildcard in there. That'll probably not end well. So, you know, you want to be a little selective there. But that's what you can do. And then you have 2 Prometheus, or the second one, of course, has a longer retention to keep the samples around for longer, and you're off to the races. The other way of doing it is with recording rules. So the federation thing, that has worked basically since federation was a thing. So that's a long time. The recording rule option is a little bit newer, basically since the evaluation interval for recording rules was introduced. So you just define a recording rule and tell Prometheus you only evaluate it every 5 minutes. That's pretty easy, right? Typically, you would want to involve a second Prometheus instance too. So you typically would want to remote write these downsampled metrics to a remote to another instance, because then you can do the retention thing again, where you have the high frequency Prometheus retains metrics for only a day or two, and then you have a longer term Prometheus for the downsampled metrics. One caveat here, if you want to not list every metric here and sort of rename it, and you think about using a wildcard here, I would recommend doing something like this here. I'm now blanking exactly on what error you get if you just try to match on the metric name, but it's an error you don't see very often. But basically, if you do this matching against the name, the resulting metric loses its name. So there's label conflicts. So my recommendation would be to do this here. You basically rename all the metrics that you have that you want to downsample, keep the original name around a label. And then when you do the remote write, you can reinstate the old name, and you have the expected label names in your long-term storage Prometheus. Right, that's it. So anybody change their mind about if they do downsampling? No? Okay. Very well. So yeah, these are the trade-offs, right, of what works today. So it works today, great. Uses PromQL, so you can do a lot fancier things than I showed you here. You don't have to do just decimation where you select the latest sample at a time. You can aggregate, you can average, you can do things over label dimensions, which is quite powerful. So yeah, it's a lot more powerful than just the sort of decimation that I hinted at. Downsides, it needs a second instance, so there's some overhead there, and it doesn't really do the delayed downsampling per se, right? You store your downsampled metrics right away, so there's some duplication, if you will. I think that's probably a pretty small downside, but still there. Okay, so let's get back to our discussion about keep interesting samples. So maybe you'll say like, oh, well, I mean, this doesn't look too bad, right? If you sort of do this over a longer term, you can see that you can get really unlucky sort of selecting the right metrics, right? So this looks, this is currency exchange data here. So, you're probably interested in these sort of outliers, if you will, right? I think this is this already hints at what we might want to do for time series data, is to select for visual representation, right? We're not really interested in getting rid of outliers in a counter because they might carry important information. Maybe you are, but then you can do sort of aggregations on the data to get rid of outliers anyway. But yeah, in other signal processing contexts, you might specifically want to get rid of outliers. So I don't think that's the case for us. So yeah, if you look at what's there in terms of algorithms to downsample data a little more cleverly than just selecting the latest in a certain time frame, there's plenty of surveys out there, so you can read up on a lot of this. But I want to highlight one that I think is quite cool. This comes out of Iceland, is a master thesis, I think, and it's a very readable paper. I recommend reading it if you want. And yeah, this specifically looks at algorithms to highlight or to improve visual representation of time series. So you get a nice overview of what's there. And then they introduce their own algorithm, a new one, which is quite nice, which I'll show you that in a second. I just want to tell you about where it came from, which is really cool. So the inspiration here is an algorithm that comes from cartography. Is basically when you want to paint a map, right? You have a coastline defined by millions of samples. and you don't really want to paint all those millions of samples, right? But you want to keep the visual representation. So they have a quite clever algorithm, which this author here has adapted to time series data, and it's called LTTB, or largest triangle 3 buckets. And this is the algorithm. Maybe I'll give you a second to read this, and maybe I can grab my water real quick. Okay. Yeah, as you can see, it's a pretty straightforward algorithm, I think. So the first bucket and the last bucket, you define there just one sample, and then you do this algorithm. For every bucket, you check which, selecting which point creates the largest triangle with the average of the following bucket. And then you get something like this. Sorry, this was meant to be, I got mixed up with my slides here. Anyway, I wanted to show you the LTTB graph first, but this is already overlaid with the decimation. So the red one is LTTB. The black one kind of in the background is just selecting the latest sample. And I think it's pretty obvious that it's a lot more detailed, while so these graphs have the same number of samples. Okay. So yeah. So where do we go with that? So I wanted to experiment with downsampling, and so I went ahead and implemented a contour command. It only works on offline TSDB data because it's much more convenient to operate on. Creates a copy, right? So maybe also a little bit to discourage people in the future to run that on live data. Basically, it uses the compaction code. It implements a custom block populator, if you know anything about the TSDB. And so far, I looked at decimation and LTTB. I ran this on my home Prometheus data. So it's like 21 gigabytes of data for a year, every 15 seconds, and downsample everything that's older than 3 months for various settings of the algorithm. So various downsampling and scopes, downsampling factors. And yeah, sadly, I have a bug in there. So I wanted to show you some result. It works. So you get the you see the expected sample reduction when you query the data and so on. But if you, I wanted to show you how much data you can save with this. And basically, I don't trust the numbers, right? There's they look too good. But I'm pretty sure I do something wrong with stitching my chunks back together and work with the index and so on. So sorry, no results. But one thing I want to show you. So this is, so these are technically results from this, so it was line. But I think this is something important to highlight for the discussion to come. So this graphs the sort of raw numbers of samples that you reduce against the data storage a chunk actually takes. So this is for a chunk that has been compacted a bunch of times. I think that's already at the largest, yeah, it's a gigabyte. So I think that's the largest chunk that you will ever get. And you can see that the chunk storage certainly does not scale linearly with the number of samples. And I guess many people expected that here. Basically, the TSDB loses compression efficiency when you downsample, right? So yeah, I think that's something we will have to keep in mind when talking about this. Oh, and you can see the decimate 12-bit. So keep only every 12th sample. There's really no reason that the index should change. So they see my likely bug right there. So that's why I didn't want to show this. Anyway, so what's next? Well, I will fix my bug hopefully, and I have a proposal coming up that outlines this. I think I'm pretty open about the outcome. I think it would be a cool feature to have, but I think it would equally valuable to collect detailed reasonings why we might not want to do this, or what alternatives should be explored. So yeah, stay tuned for that. So what do we learn today? Downsampling. We talked about what we probably mean with downsampling, or if you have other opinions, I'd definitely like to hear about that. Counters are pretty easy to downsample, and I think histograms too. Gauges, not so much. I introduced you to a pretty cool algorithm, I think. And yeah, definitely one thing that's pretty obvious already is that fewer samples definitely decrease the compression efficiency. So the more you downsample, the lower your return on storage savings is going to be. Not to mention that the index overhead should really not change if you only reduce your sample rate. It would if you downsample across label dimensions. So that's why I think that's an interesting thing to explore as well. And with that, I'm a little early on time, as usually is the case. Thank you, everybody. And
thank you. You also get an orange knife.
thank you.
Okay, our schedule already says we're in the break, but are there one or two quick questions? There's one? Okay, let's do one or two max.
Thank you for the talk. A short question. This triangle algorithm, does it, if you apply it, does it change the distance between data points?
It changes the time distance, yes.
Yeah, but doesn't it break some bronchial promises when calculating rates, or I don't know, like some hour time?
I don't think so. I mean, samples can be missing from scraping as well, right? So the actual timestamp doesn't change. It's just that the distances become unequal. But that probably plays into the loss of compression efficiency as well. Yeah.
Okay, thanks.
Yeah, it's like if you had a weird Prometheus server that scraped at kind of jittery times and stuff, I guess. Okay, one last question.
Yeah, nice talk. You mentioned that counters are easy, but don't you think that at some point you will start losing reset information and then it kind of distort the signal? So you will kind of need metric type to know how.
Yeah, of course. There's multiple downsides that I didn't want to go into that much detail. That's for the proposal. You also have to take care of how you query this data, right? You can't, if you only keep a sample every 2 hours, you can't run a rate over 5 minutes, right? Things like that. So there's definitely caveats, but I think the way people expect to query downsample data, it has some of this stuff already built in. I don't think anybody will run a 5-minute rate over sort of historical downsample data, right? And if they do, then they shouldn't expect to get anything reasonable out of it, I think.
All right, thank you so much again.
Thank you.
So yeah, there's a break now. Let's be back here at 11:50.